Assalamualaikum and good day everyone. Now we are going to continue with week 15 of the lecture, okay, about memory device. So this chapter is more about reading, okay. I mean it have a lot of reading. You guys can read on your own, okay. I will do summarization. I will focus on the examples, okay. Otherwise this will be long, okay, if I to read one by one. And in order to help you guys that doesn't have the module, I will continue to teach using the module, and hopefully you have the a bit sufficient view, okay, of the module pages, okay. So now we are going to memory device, okay. You can pause the screen in order for you to read, okay, the pages. So okay, we have in under the chapter 14 memory device, okay, we can start. Okay, up to this point we have covered only fixed type logic device. The function is fixed during manufacture and cannot be modified. This chapter and the next cover logic device that is configurable by the user, means we can configure the function, okay. So they can logic device fall into three broad categories, okay. It's shown in figure 14.1. We have fixed logic, okay, they can be used straight away. They can be of two types, off the shelf or custom, okay. Off the shelf device are components that you can find in catalog and available to anybody. Custom device are components that are designed for a specific customer. One example is a microprocessor tailor-made for specific type of mobile phone. Such a device is based on the specification of one phone manufacturer and not made available to the other manufacturer, okay. So the second category is memory device. They are devices that store data and computer program, okay. So we will cover this memory device in this chapter, okay. So you see here there is three types of logic device. We have the fixed one, off the shelf, custom, and then we have memory, which is a RAM, random access memory, and read only memories, okay. You will see later on, okay, in the next pages, okay, subsequent pages, RAM and ROM, and then you have PLD, SPLD, CPLD, and FPGA, okay. So next we go to the memory, okay. I go a bit faster because this chapter is a lot of readings, okay. You can read, okay, at your own pace, and I want to focus more, like I say, on the examples, okay. It's better to understand, and then make sure you guys read carefully, because okay, because the question can ask about the definition and everything, okay. So let me do it a bit higher, okay, so that you have a full view, better to cover all the pages, okay. I hope this is fine, okay, but it will be a bit smaller, sorry for that, okay, because I'm trying to, for you those that didn't have module, okay, I'm trying to help you guys, okay. So type of memory device, we have memories, which is a RAM, random access memories, volatile and non-volatile. We have under volatile, we have SRAM, DRAM. Non-volatile, we have BRAM, FRAM, MRAM. And then read only memory, we have non-programmable, okay, ROM. One-time programmable, the word self-explanatory, it can be one-time program only, and then it can be programmable many times. It is EPROM, EEPROM, and Flash, okay. So memory device falls under two broad family, which is random access memory and read-only memories, okay. Random access memory is volatile, means that once the power cut off, all the information is lost, okay. This is the RAM, okay. ROM is always non-volatile, okay, meaning it will also hit data when the power is removed. The data is still there, okay. So as shown in figure 4.2, okay. So figure 0.3, okay, you guys can read on your own here, okay. Figure 14.3 shows the input and output of a generic memory chip, okay. So this is your figure 14.3, okay. Hopefully it's still okay, okay. So data input line and bits of data that is going to be stored into the device. So you have n bits of data input, and then you have data output line, n bits of data retrieve. Okay, one is going to be stored and data output is going to be retrieved from the device. Address line, k bits, which identify the location of data to read or write. Read signal indicates a read operation when asserted. Okay, means it will read the operation. And then write signal is indicate a write operation when asserted, means we're going to write some information. We put some information. Okay, a group of data input or output lines form a data bus. Okay, some devices combine multiplex the input and output lines to reduce, okay, to reduce the pin count. Sometimes we can use a multiplexer. Okay, a group of address lines form an address bus. Okay, so if you can see here you have this data input lines n bits, and you have an address line k, and memory unit of 2k words, n bit words, and then we have read and write function. Okay, then this is your data output line. This is example for 4 times 3 memory. Okay, so you have 2 inputs and you have 3 outputs. Okay, to the memory array and from the memory array. Okay, then this is the function. So you have you have 4 address. Okay, you have 4 times 3. Okay, a unique information transferred at the same time on the data bus is known as memory word. Data in a memory device is organized in a bit matrix 2k times n, where 2k is the number of words in the device and n is the number of bits per word. Okay, I think this one is self-explanatory, how many bits in the word, and 2k is the number of words. Each word is assigned an address from 0 up to 2k minus 1. So this, for example, figure 14.4 here, okay, show the typical content of 4 times 3 memory units, where k is equals to 2. Okay, k is equal to 2 means 2 to the power of 2, 4 minus 1 means that from 0 up to 3. From 0 up to 3. Okay, and n equals to 3. Okay, 3 bits per word. Okay, during a read operation, this sequence of events occur. Okay, computer give memory address and read that signal. Memory receive address and output data to output data lines. Computer reads data from data bus. Okay, during write operation, this event occur. Okay, during the write, okay, operation. So we have read and write. Okay, so you need to able to distinguish this operation. Okay, so in the read write operation, the computer give memory address, data, and write signal. Okay, memory store data into a memory location. If no read and write, the memory device stay idle and holds on to the previously stored data. Okay, if we don't do any read or write, okay, it will maintain the previous data and it's remain idle. Okay, idle is like it's on, like it's active, it's waiting to for next instruction, whether read or write. Okay, is idle is not off. Okay, now the next we go to the comparison between static RAM, okay, static random access memory, and dynamic random access memories. Okay, you guys can read these informations. Okay, for those that didn't have module, you can always pause the screen. Okay, let me try to adjust. Okay, so you guys can read this for detail. I will go for this for explanation. Okay, static RAM contain fewer memory cell per area. Okay, while dynamic area have higher density. Static RAM have lower access time, so therefore it is faster. Okay, so dynamic RAM access time is greater than RAM. Okay, static RAM is each bit is stored in a flip-flop. Dynamic RAM, each bit stored as a capacitor charge. So different. Okay, different how it is stored. Okay, static RAM refresh circuit is not required, and dynamic RAM, however, refresh circuit is required to maintain capacitor charge. Okay, because we want to to maintain the charge and capacitor, so we have to refresh the circuits. Okay, static RAM costs more per bit of data, and dynamic RAM is cost less. So this one is expensive, and this one is cheaper. Okay, so this is the size comparison. Okay, between various type of read and write memory. Okay, of course this one is not to scale, just to give you overview. Okay, if you see the size comparison for various type of read and write memory, you can see DRAM have the least one, intermediate is your SRAM, and then the biggest one is the register file, because it is 2k times n. Okay, so which is big. So you guys can pause the page and read. Okay, because the important is how you because if I'm going to explain word by word and also the explanation, we may have more than 1 hour per video, and I'm worried my handphone will automatically shut down, stop recording, then I need to start from zero. Okay, so it will not be very good for me, and also it's not very good for you to listen to a very long lecture. Okay, next we go to the ROM, read only memory. Okay, strictly speaking, ROM refer only to mass program, okay, which is MROM, the oldest type of solid state. Okay, which is programmed into integrated circuit by the manufacturer and thus can never be modified. Okay, ROM is a bit limitation if you want to read write. Okay, however, we can have a different, whether it is a non-programmable at all, whether it's one-time programmable, or it can be programmable many times. Okay, but it's limited in we want to program it. Okay, so here you can see we have MROM. Okay, MROM, OTROM. Okay, MROM mass program read only memory, OTPROM one-time program read only memory, EPROM erasable program read only memory, and EEPROM electrically erasable programmable read only memory. Okay, I think you guys can read this and understand quite straightforward. Okay, next, I think this one is popular already, the flash memory. Okay, the flash memory is just like what we know. Okay, so it's a high speed and high density. This device erases many locations simultaneously. Although it can be read and written without a special device, it cannot replace RAM because it is slower than RAM for write operation. Like EPROM and EEPROM, flash memory can only tolerate about 10,000 erase operation before the device fails. Okay, so the flash memory actually have limits. Okay, you guys need to know this. It cannot be erased and cannot be erased and write for unlimited in infinity. No, we have limit for it. Okay, this is, I think, if you guys this flash memory is the one that we know of. Okay, commonly used. Okay, all type of ROM except for MROM are field programmable, meaning they are programmable outside the factory. Okay, means it can be programmable outside. Field programmable ROM are simple PLDs, programmable logic device, to be covered in the next chapter. You will see later on. Okay, are the program device programmed using device programmer. Okay, such as the Gallup 5 shown in figure 14.7. Okay, so this is how we used to program a ROM. Okay, I think I have been exposed to this one during my degree. Okay, I see it and we learn how to burn it. Okay, so we use the word burning. Burning is like here. Okay, burn is that we want to program the chip. Okay, so we burn it. Okay, so you put the chip on top of here. If you know the chip have its leg, right? So you put on here and then we lock them. Okay, you see the lock here, and then after that when we finish, we unlock, then we take it out. Means that time is already burned. Okay, so a bit pity that because due to pandemic or this ODL, okay, you guys didn't see this okay thing. Okay, for EPROM, another device is required. This is the UV eraser, which erases the EPROM before inserting into device programmer. Okay, flash memory and EPROM can also be programmable in circuit without having to remove the chip and place in the burner. If the system has the necessary program circuitry, this property is known as in-system programmability, ISP. Okay, So okay, let me, okay, for those that doesn't have the module, again I try to adjust so that you have the full view. Okay, so far so good. Okay, now next we go to the 14.4, which is the ROM implementation of logic function, the read only memory. Okay, ROM is often used to implement lookup tables, okay, which is LUTS. Okay, LUTS convert from a set of input patterns to the corresponding set of output patterns. Okay, so you see here, you see the important word, it's convert from a set of input pattern to the corresponding set of output pattern. Okay, so input and output. In some application, the time to access memory can be shorter than performing complex computations. Okay, so you see this figure 14.8 introduced the alternate notation for high-end devices, and you need to see the notation, the difference marking. What is the meaning for them? Okay, this one, I think this one is pretty separate. This one means no connection. This one is mean fixed connection with the dot. This one is the cross means it's a programmable connection. Okay, and if you see, this is your ABC as your sorry, as your like input, and you have this. Okay, this is a buffer, right? Then this one is a direct buffer, means the value is maintained A, then the output is A, and you have bubble here. So we have A and A bar, B bar, and C bar. Then you have AND gate, then you have a OR gate. Okay, then if you guys see, okay, you guys can try yourself. Okay, you can see for here, let's say for example A bar, B, C bar. Okay, so you can see, where is it? Here, A bar, B bar, C, A bar, B bar, C bar here, and then plus A, B bar, C bar, F. So it's plus here in order to get the function of F. Okay, then figure 14.9 shows the schematic for 32 times 8 ROM using the hyphen-in notation that we just introduced. So from here, okay, we show the we translate to our 32 times 8 ROM. Okay, so you see you have A0, A1, A2, A3, A4. This is 5 to 32 decoders, means you have 5 inputs, then you have 32 possible outputs. Okay, so here if you see, we have D7 until D0. Okay, so it's 5 to 32. Okay, if you see here, we have 5 input and 32 output. You see 0, 1, 2 until 31. Okay, and here you see it is D7 until D0. This is how we're going to describe the function that we want. From here you can see, right, D7 is what? Okay, so we go to the exercise. Okay, implement the following Boolean function, okay, on an 8 times 4 read only memory. So we have W, A, B, C, the variable inputs, and this is the min term 2, 3, 4. Okay, the rest also the same. So you need to I hope you guys always remember. Okay, M is a min term, then if the capital M is a max term. Okay, so I think by now you already expect already. I believe so. I believe so, or I hope so. Okay, so solution, the logic expression are first mapped to the truth table as in figure 14.10a. Okay, here. Okay, first you translate this first into your corresponding truth table. So you know that you have ABC as your variable input, so you list down your ABC possible value from 0 until 7. Am I correct? Then you have A2, A1, and A0 as your inputs of your 8 times 4 ROM. Okay, and then you go for the corresponding value, like for 0, 0, 0. Okay, for 0, 0, 0, what is the value? 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, is y. Okay, you guys can see right here, 0 y. Okay, and so on. Okay, and then you have, and then you design the assignment of the pins. Okay, assignment of the input with the chip. Okay, with the ROM at times 4 ROM. So you have A is A2 here, B to your A1 pin, C to your A0 pin. Okay, so you have A, A2, B, A1, C, A0. Okay. Then you have the output W connect to D3, X, Y, and until Z correspondingly. Okay. So we have here the ROM implementation of the 4 Boolean function. Okay, because we have output of W, X, Y, and Z. Okay, so here is X, Y, and Z. Do you agree? Like, because this is W, so W, X, Y, and Z. Okay, in order to have the function of output W, you know it consists of 2, 3, and 4. That's why you have programmable here 2, 3, and 4. The same goes for X. Okay, you have 3, 6, 7. That's why 3, 6, 7. Again, this one is 3 to 8 decoders. Okay, you can see, right? 3 to 8 decoders. Okay, so this is actually the programmable connection. Okay, next. Okay, so example, use a ROM to implement a table of squares. Now, table a square, what do you understand by square? For example, 0 square is what? 0, 1 square is 1, 2 square is 4. Okay, of course this is base 10. Okay, just for me to make you understand it simple. Okay, 3 to the power of 2 is actually 9, and so on. Okay, use a ROM to implement a table of squares for input from 0 to 7. Example, output is the square of inputs. Okay, solution to implement a squarer circuit. Okay, means the output will be the square of your input. We will need 3 inputs. Okay, P2, P1, P0. Why? Because you see from 0 until 7. Okay, 7, this one is actually the base 10. Okay, so 7 square is equals to 49. So you need to know what is the corresponding value for 49. Okay, so where is your base? Okay, 49. If you want to see the binary equivalent, okay, so it is 11000. Okay, we have this 1100001. This is equivalent to 49 to the base of 10. Okay, so you can see here 1100001. Okay, so it must be able to represent output, okay, from 0 to the power of 2 until 7 to the power of 2. Okay, by inspecting the truth table, we can also see that the output Q1 is always 0, so Q1 is permanently grounded. Why? Because you see here is 0, and you can see the output of the Q1 is always 0. Okay, you can see from here. So if you see this one always 0, you can connect it to the ground. This is very important, okay, for you to do the simplification, and because this will be involving will be muchly related to your design question. Okay, so if you know if 0 you always all the time, you can connect it to the ground, okay, for your outputs. Okay, and then if always equals 1, you can connect it to the source, for example the VCC. Okay, so Q1 can be permanently grounded. Similarly, output Q0 is always the same as input P0. If you notice, Q0 is always the same as P0. Okay, you can see, you can relate 0, 0, 1, 1, 0, 0, 1, 1. So they are always the same. So if they are the same, we can connect Q0 directly to P0. You can connect output Q0 directly to P0. Okay, so this is shown in the figure 14.12. Okay, you can see it very clearly, where Q1 is just connected to ground, permanently grounded, Q0 directly connected to your P0, and then by then we have Q2, Q3, Q4, Q5 only. Okay, that's why you can use 8 times 4 ROM. Okay, I mean this is one of the way of design with 8 times 4 ROM. Okay, for the square circuits. Okay, I think it's quite straightforward also. Okay, it just help you to understand, okay, what is the is it about. Okay, now the memory bits are programmed into ROM according, okay, this one is according to ROM, according to the table and circuit as shown in figure 14.13, which is on the next figure. Okay, now inputs A2, A1, A0. Okay, you have of course 0 until the 7. Okay, means 0 until 7 just now. And you can see D3, D2, D1, and D0 as your outputs. Okay, D3, D2, D1, D0 as your output, because you see in the ROM you can only have 4 outputs here: D3, D2, D1, D0. I mean the available pin. Okay, so that's why you put it here. Okay, and then you do the corresponding programmable connection. Okay, corresponding programmable connection. Now for D3, D2, D1, and D0, if you notice, okay, we have 1, 2, 3, 4, 5, 6 outputs. However, okay, because of this simplification, okay, these 2 outputs is connected directly, whether like Q0 to P0 and Q1 is grounded. So we only have to settle for the 4 outputs. Okay, so the 4 outputs here you can see is D3, D2, D1, and D0. D3 is 6 and 7, okay? And then D2 is 4, 5, and 7. D1 is 3, 5. D0 is 2, 6, okay? Okay, you can see, for example, here D3 is connected to your Q5, which is this is your D3. If you see D3, because Q5 is connected to D3, you can see is to the input of 6 and 7. Okay, that's why it is 6 and 7 here. Okay, and the rest are the same. Okay. Next, we go to the last part, which is the memory integrated circuits. Okay, so JEDEC solid state Technology Association, formerly known as the Joint Electronics Device Engineering Council, JEDEC, established industry standard for integrated circuits. This include the pinouts of popular memory device. We will take a look at 3 chips, whether 62, 64 64K bits SRAM, 27C64, 64K bit EPROM, and the 28 64-bit K-bit EPROM, as shown in figure 14.14. Okay, this device each contains 64 kilobits organized as 8 kilowatts times 8 bit. Okay, they all share common pin out for supply. You can see VCC, this one is common, VCC and ground is common. Okay, all of them have VCC and ground. Okay, address bus, we have A0 until A1, until A11, we have the same common, and data bus D0 until D7. So all of them have this common pin that we discuss. You can read from here. Okay, so how I'm going to show this at the same time you're able to read I am sorry, I tried my best. Okay, so this device is content. Okay, you guys can see the address bus has 12 pins to uniquely identify 2 to the power of 12 218192 different memory location. Okay, they differ only control signal. Okay, so let us take a look at the 6264 SRAM static random access memory. It has the following unique pins. Okay, this one is 62 64 SRAM. Okay, so this is the unique pins. We have NC non connection, so we don't have any connection here. WE write enable, active low signal to indicate a write operation, means we program it, we put the write we put the data into it. OE is output enable, active low signal to indicate a read operation. CS1 chip select 1, okay, when low together with CS2, high together with CS2. Okay, it must be with CS2 in order to enable the chip, so must together with CS2. We need CS2 and CS1 together to enable the chip. Okay, CS2 chip select 2 when high together with CS1 low. Okay, enable the chip. Okay, to enable the chip for read or write operation, the chip must be enabled. This is done by simultaneously giving CS1 low and CS2 high, just like the table shown here. Okay, now to enable the second device is the 27C64 EPROM. It has the following unique pins. Okay, so each of them have unique pins. So they are actually discussing the unique pins for each of the JEDEC memory chips. Okay, this is for 27C64. Okay, we have VPP, programmable voltage, high voltage to enable memory bits to be set. OE, output enable, active low signal to indicate a read operation. CE, chip select. When low, it will enable the chip. When PGM program, when low indicates a write operations. Okay, you need to see the different pin that in charge for write or read and another different function. NC, no connection, means this one is not used. Okay, to enable this chip for operation, the CE pin here, okay, is pull low. You need to be low to enable the chip. Okay, to program the device, the chip is inserted into a special EPROM EEPROM programmer. Okay, if you want to program the device, to program the individual bits, the PGM pin is pulled low together with the appropriate voltage being applied at VPP. Okay, here, appropriate voltage. If you want to program the individual bits, okay, so the PGM is pulled low. What is the PGM here? PGM is, the name is program. When low, it will indicate a write operation to this 27C64 EPROM. Okay. The last device is the 2864 EPROM. It has the following unique pins. So this is your 2864 memory chip. JEDEC memory chip. Okay. So the following unique pins. Okay. WE write enable, active low signal to indicate a write operation. OE output enable, active low signal to indicate a read operation. CE chip select, when low enables the chip. And we have also another, the same pin, which is NC, which means no connection. Usage of the OE, CE, PGM and VPP are similar to the 2764 device. The device is writable, unlike the 2764. However, to enable a write operation, the WE pin is pull low. Okay, it must be pull low to indicate a write operation. Okay, so with that we finish the chapter of 14 of memory device. Okay, this is the exercise. You guys can try it out. Okay, I suggest you try it out so that you can test whether after you read the chapter, you can test your own understanding. Okay, by doing the exercise. Okay, with that I'm finished the lecture. We will continue the next lecture in the next lecture video. Okay, Assalamualaikum and good day.